So lastly, I already talked about the electric field and also their free energy. Now that we're talking about the anti-semiconductor. So in this case, semiconductor normally they are the insulator. They cannot move itself, so that we have to put the impurity. Impurity. The reason to put in the impurity means that here we have the energy state, then we have the conduction band. This one is a forbidden gas. And that one we just have balance band. So normally this atoms are structured like this. So in the balance band got the electron. So electrons are prevented by the forbidden gas not to go to the conduction band. When the electron go to the conduction band, so that they can move freely. So that this valence band is the forbidden bands make the prevention. So therefore the energy level. So you want the electron to move out, you have to provide the energy level. So in this case, energy level, you have to put the energy level. For this transistor, you have to give the biasing voltage between the voltage between the base to emitter, and then this can reduce the forbidden gas. So in this case, some of the electrons we want to reduce the usage of energy. The best thing is that you have to narrow the forbidden gas. You have to narrow the forbidden gas. So how to make the narrow forbidden gas? We have to put the impurity. So impurity affect the conductivity and also they can narrow the forbidden gas. So this is the way that we have to put the impurity. So the impurity affect the conductivity. And also the electron and positive hole motion are made to their conductivity. Electron and positive hole motion make to their conductivity. So how you make this conductivity? So in this case, you should see here this one with this conduction band. Here with the valence band. Here is a forbidden gas. So here into the forbidden gas, we can place a energy extra electron. So that this extra electron, by putting the extra electron, we can narrow the forbidden gas. Also, they encourage more electrons to passing through the forbidden gas. So this is ways we are making this constructing the semiconductor. So semiconductor, the way is we have to put the extra electron, putting the extra electron into the semiconductor. So this extra electron we can put into this energy bond. This is the energy bond. They are atoms are bound together. This atom, they are bound together. So this bond together, we can put the extra electron here. So this is the extra electron. So by putting the extra electron, this is the atomic structure. You put the extra electron in the atomic structure, and for the energies then we can put the extra electron into the valence band, forbidden gas. So this is the way electron waves are moving. So in this case, the electron we got the energy. This electron's energy can be calculated. So E and Z is equal to minus m e power 4 divided by the 8 n square, a square Q0 square and then QR square. So this is the equation that we have to write. So in this case, N is the number of parts. N is the number of parts. M is the mass of atom. E is the charge of electron. So this is Q means the initial state. Charge and QR means the charge at the R state. So this is the way that we can write out, and this case H is a Planck constant. So the energies are possessed by the electron can be calculated. En is the electron energy. So by putting the extra electron, the energy level can be changed. This energy level can be calculated by this equation. So in this case, for the hydrogen atom, this E will be 13.6 eV. So for the crystal atom, then we can calculate the equation. So this is the way we can calculate the energy possessed by the electron state. So that's energy equation. So in this case, electrons semiconductor can be transformed into mobility. Mobility means the quantitatively is depending on the mobility. How much of free electron and how fast they away from moment determine the mobility. So the quantity depending on the mobility. Conduction depends on mobility of free electron. So in this case, you see the Jamesians semiconductor and the silicon semiconductor. So the silicons are better than the Jamesian because they got more free electron than the Jamesian. In the meantime, their mobility will be higher. This mobility can be calculated. The equation to calculate the mobility is V squared to the mu multiplied delta. So this is the mobility equation. So in this case, the V is equal to the drift velocity. That will be the centimeter per second. And theta is a free strength. And mu means the mobility. The unit will be the centimeter square, 2 power minus 1 and the second power minus 1. So this is the way that we calculate for the mobility. So in this case, the mobility means that drift velocity. When the field is charged to the electron, so electron will be moving. So the moving velocity, the drift velocity, is depending on the how much mobility, how much mobilized electron in the area, and also the free strength. When you put a free strength, then we get more mobility electron. So the drift velocity will be higher. So this is the way we can calculate for the mobility. So in this case, this free strength for the p-type and n-type semiconductor can be calculated. So this data is really delta n plus the delta p. Delta n means this is an n-type semiconductor free strength, and delta p means a p-type semiconductor free strength. So delta n, n-type semiconductor free strength. And the delta n, so delta p means a p-type semiconductor free strength. So we can also calculate the delta. Delta is the p-type semiconductor free strength, and the n-type semiconductor can also be calculated. theta is also equal to E multiply Ni mu N plus Ni mu B. So this is the equation to calculate. So this is the number of the conductor. In this case, number of the p-type crystal and the n-type, that will be the Ni. So Ni p-types are atoms and the n-types are atoms. This is equal to the Ni. E is the electron charge, and the mu N and mu B means they are the mobility of the n-type and the p-type semiconductors. So mu B, mobility of p-type semiconductor, and then mu N, mobility of n-type semiconductor. So those are how the p-type and the semiconductor, n-type semiconductor are working, and how will the mobility and how the force are affecting. So by this way we can calculate the those equation. So in this case, normally this is the conduction of forbidden gas. So that this forbidden gas prevent the electrons to move. So that we have to put the energy, or we have to put the impurity. So by putting the impurity extra electron in the forbidden gas, so electron will be energized and we encourage the movement. So that time we put the energy, electron can be moved easily. So this energy level requirement can be calculated by this equation, minus m e power 4 divided by the 8n squared, a squared, q0 squared, and qr squared. So that when the electrons are moving, they possess the mobility. So they possess the velocity. So velocity depending on the mobility multiplied with the free strength. So the free strength is the combination of the n-type and the p-type semiconductor. Theta is the delta m plus delta p. So this delta can also be calculated E multiplied Ni mu m plus Ni mu p. Ni is the number of the p and n-type atoms. So mu B is the mobility of the p-type semiconductor. Mu N means the mobility of the n-type semiconductor. So this is the semiconductors. They are having those equations, and they following the equation to more. So in this case, sometimes we have to make the recombination. Recombination means when the supply, we stop the excitation supply, the semiconductor will stop the conduction. This means all the electron and the hole will be recombined. The recombination, this means removing the field, the recombination can happen. So generation and the recombination. So because of the vibration of the energy, because the variation of the energy in the crystal lattice at the room temperature, covalent bonds are continually being broken. So this process is a electron hole generation. This means at the room temperature, so those electrons are divided by the bond. So this is the binder of the bond. Those bonds are we call the covalent bond. When the bonds are broken, the electron will be free. So electron will free. So that once the electron coming out, hole happen. Hole got the positive charge, electron got the negative charge. So electrons are moving from the one atom to another atom. By this way, electric current will flow. So the electron coming out is broken of the covalent bond. So these covalent bonds are when they are at the room temperature, broken of the covalent bond, causing the electron to move out, and the hole can happen. So the more hole, there will be the positive particle, and the more electron, there will be a negative particle. So the n-type, p-type semiconductors are one got a positive, another got a negative terminal. So when these holes are when we are external holes are stopped, so those holes will be rejoined, and the electron and the hole will be recombined. So this is the way the electron and the holes happening because of vibrational energy of crystal lattice. At room temperature, covalent bonds are continually being broken. So this process is electron hole pairs generation. So this process is the electrons hole pair generation. So the electrons are being recaptured by the unfilled bond. So in this case, some bonds are broken and the electron coming out. Some electrons are moving. Some electrons are recaptured by the unfilled bond. So the electrons are being recaptured by. Electrons are being recaptured by unfilled bond. So to produce a recombination of electron and both pairs. So this is the generation and recombination are happening at the same time. At the room temperature, when this is the bonds are vibrating, so bond will be broken. Vibration means that we are charging the external energy. By charging the external energy, the crystal bonds are broken and the electron coming out. So the those electrons are will move away. At the meantime, some of the electron will be recaptured by the empty bonds. So this is the recapturing and also the recombination and the generations are happening at the same time. When the generation rate is greater than the recombination, the electron will be the accumulation of the more free electron and the electrical charge will be the flowing. But the recombination is greater than the rate of recombination greater than the generation, so the all free electron will be gradually decreased and the bond will be stable. So this is the way we making the energy. So this means that how much free electron coming out generated and how much recombination depending on how much energy you put. You put more energy, more vibration, more bond will be broken, and more electron will coming out. Less energy, so less bond will be broken and there will be more recombination. This means that you have to get the appropriate electrical field excitation so that once the excitation is removed, so that there will be recombination can happen. So this is the inside the atomic mechanism structure is happening like this. So in this case, valence means the number of the recombination and generations are equal. This is the valence state. The valence state can be the electrically equilibrium and thermally also be equilibrium. Electrical equilibrium means that no electric current flow. Thermal equilibrium means that no heat flow. This is the balance saturation. The balance saturation can also be explained. It's a common for the both electrical and the thermal flow. Balance. So balance means so that it is set up between the generation and recombination hole and the electrical energy. It is set up between generation and recombination. Hole and electric energy. Hole and electron density. Also also causing the thermal equilibrium. So this is what thermal equilibrium can happen. So this is the way the recombination and the thermal equilibrium happen. So in this case, we also calculate the energy density. So energy density of the state in the energy band. So this is we also talk about the density of states in energy band. When the energies are bent, this means that the conduction band stays, so that all electrons are moving, so they also got the energy density. So in this case, passing of the electron from the top of the valence band to bottom of conduction band require the expenditure of the least amount of energy. This means the electrons are happen at the top of the band, so that you need a little energy. So this means that but electrons are in the valence band, you need more energy. So this means that the passing of electron from top of valence band to bottom of conduction band. Require the expenditure of this amount of energy. This means that the electrons are happening at the valence band. They are actually in the valence band, so that you get that for the semiconductor, you get a little energy. This one will go to the conduction band, so on the conduction band. So the electrons must be located at the top of the valence band, so that when you give it a little energy, it will go to the bottom of the conduction band. So we have to make the design. Most of the semiconductors electrons are located at the top of the valence band. They are always arranged at the top of the valence band, so that when you give it a little external energy, they will easily go to the conduction band bottom, and then they will move out. So this is the density state. So number of the electron movement between two bands depend on the temperature and the energy. So how much electron will be moving? How much electron will be moving from the valence band and the conduction band? This is the amount depend on the energy as well as the temperature. This means that when we are working in the electronics equipment, the room temperature is important. Because of the room temperature different, the amount of the electron flow will also be different. So this is why we have to keep the electronic equipment at the particular temperature. The design with the 25 degree, you must keep the 25 degree. That temperature is higher than that amount, more electron will be moving out. More electron will be moving out means the circuit operation will be undesirable. So the more current will flow, the more voltage signal will happening, so that it cannot be controlled. Starting out of power. Therefore, we have to keep the electronic equipment in the starting temperature. The reason is the amount of the electron passing through from the one state to another state, not only depending on the free energy, but also depending on the room temperature. So the number of electrons moving between two bands depend on temperature and energy. So this is why electronic equipment we have to keep the starting temperature, because when the temperature change, more electron will be moving, so the circuit operation will be the undesirable effect. So the electrons are now will be moving. So in this case, how much of possibility? You also have to know about the probability. What will be the probability and what will be the probability of the moment? Those things have to be know about. So in this case, we also have to calculate the probability stage. So that we calculate the SE. M means this is the number of electron stage. So this for the energy difference level. Energy difference level. This is the M. M can be calculated. The formula is 2 power 9 by 2, M power 3 by 2, pi divided by the 3h squared, E minus EV power 3 by 2. So this equation. So this equation means that M is you know that mass of the atom, A is a Planck constant, EV means the valence Bohr energy, E means the energy at the conduction band. So the energy difference with the M can be calculated. So that the rate of the change of the energy difference is the SE. So we differentiate how much the energy difference rate. When you charge the energy, this means that you are moving changing the energy difference. So that how much energy difference is happening with the rate of the change of the energy difference. Rate of change of energy difference. So that can be the SE. SE formula is dm by dE. We differentiate. Differentiation means that finding the rate of the change. So SE equal to dm by dE. So in this case, that equation that you differentiate what you call it 2 power 7 by 2 multiply m power 3 by 2 E minus EV power half divided by the h squared. So this equation we got. So this is the SE. SE means the rate of the change of the energy difference. This rate of the change of the energy difference, we causing the energy amount of the electron with moving. So in this case, how much energy possibility? How much probability? This means how much valence electrons are happening, how much valence electrons in this state. The more the valence electron, the more possible to flow the more electrical current. The less the number of the electron, less possibility to flow the electrical current. This means the probability also affecting the amount of the electron flow. So this means that we can calculate. So in this case, we calculate it this way. So energy density. So energy density means this is SE multiplied DE multiply SE and the DE multiply. This means the total number of available state in energy range. So this means that DM. This equation SE is to DM by DE. So SE multiplied DE will be the DM. DM means the total number of available states. In energy rate. DE. This means that when you change the energy, how much available state? How much available state means that some electron will be the free state, some electron will be the captured state. So that how many available state can be calculated by the energy density equation. So this is Fe multiplied DE equal to the total number of available state in the energy range. So here will be the probability Fe. The probability of the state. Probability so that state means how much possibility to occur such number of the states. So this is the FE. So in this case, NE. NE means small energy range. So now we can draw. So this means we can also calculate the Fermi factor. Fermi factor is this is for we draw the graph. This graph means here with the energy. Horizontal with the FE. FE the probability. So energy and the probability we can draw. So this probability we also call the Fermi factor. Fermi factor is how much of probability of the state, how much of state can happen, how many states can happen, this is the probability. So that this Fermi factor and also the energy can be drawn in the graph. This graph will be like this. So this becomes graph like this. So this becomes energy is increased, Fermi factor increase, so energy will increase in the way these are drawn like this way. So in this case, we know that the Fermi level means how much possible electron, how much possibility to break out the fire, or how much possibility to the electrical current flow. This is the possibility. The possibility is that we also call the Fermi factor. The more Fermi factor, the more possible states for the electron current to flow. So this Fermi level also determines how much energy and how much energy will be required to move out the electron. This is we call it Fermi level. The Fermi level is energy where the probability of state being occupied. Energy where probability of state of electron states are occupied. So this is we call it Fermi level. So that we in the conduction band, when the electrons are moving in the conduction band, so we can calculate the equation conduction band. So in this case, 1 minus Fe is equal to probability of the positive hole. So the electron and the holes are the combination. So the one electron out, there is one more hole will happen. And one electron will increase, one hole will be less. So this is the electron and the holes are the positive negative. So this is the 1 minus Fermi level. Fermi level is the possibility of electron. So 1 minus possibility of electron, you got the probability of the positive hole. So the positive hole and the negative electron are related to this equation. 1 minus Fe equals to the probability of the positive hole. So this is the conduction level situation. And therefore we can draw this the Fermi level with the temperature. This Fermi level is changing with the temperature. Variation of Fermi level. With temperature. So that we can see that the semiconductor, one with the intrinsic semiconductor. So intrinsic semiconductor, what will happen is this one is the conduction band. So at the bottom of the conduction band, the electrons are already here. This is the bottom of the conduction band. So that will be the Fermi level, EF level. When the energy is more than the EF level, electrons are coming from the valence bond, they are reached to the conduction bond. So here we have the valence bond. So that when the electron here, two electrons coming out from this one, whenever the electron less, then what happen? The holes are happening at the top. That kind of conductor means the intrinsic semiconductor. This means the electrons are already at the conduction bottom, the conduction level, so that by putting the extra energy, they will be moved out. So they will are ready to move out. That kind of semiconductor, the intrinsic semiconductor. And then another we type the anti-semiconductor. For the anti-semiconductor, there will be the electrons are they have got the more conduction and they are happen like this. There will be the conduction there. And also the holes are in the this gap, and there will be the positive charge here. So in this case, we put that more hole into this state. This is the donor state. So in this case, this semiconductor with the anti-semiconductor. In the meantime, we also see the p-type semiconductor. So in the semiconductor, there will be the conduction band. And here we will electrons and the whole combination that we put here, there will be the positive. So there will be the valence bond here. So this is the p-type semiconductor. So the intrinsic semiconductor, anti-semiconductor, and the p-type semiconductor, their energy bonds are related to this diagram. Okay, as this is we are talking about how the energy bonds happening in the state. So there will be this p-type and semiconductor. We explain for the p-type and anti-semiconductor. For all the p-type and anti-semiconductor, they all got the CI, the conduction band, forbidden gap, and the valence bond. So that we have to narrow this gap. To narrow the gap, how to narrow the gap? You have to put the extra electron. By putting the extra electron, we narrow the forbidden gap, and the electron will flow. So the number of in this case we need to get the extra energy. This energy can be calculated by the equation minus me power 4 divided by the 8n squared, a squared, q0 squared, and qr squared. So the electrons are moving. So two electrons got some velocity. Velocity is mu multiplied delta, mu is the p strength, and then mu is the mobility. So that all the electrons are moving. They got the n-type and the p-type are free. So the n and p-type combination delta is equal to delta m plus delta p equation. So the generation and recombination can happen. Sometimes the electrons are coming out, and sometimes will be recombination. So the generation state is more than the recombination, electron will flow out. So the balance means the sum between the generation and recombination whole electron density. So the density of the state energy band can be calculated. The equation will be here. So m equal to 2 power 9 by 2 and power 3 by 2 pi e minus ev power 3 by 2 divided by 3a squared. So the rate of change of the energy difference is that we differentiate. By differentiation that we call this equation. So the SE multiplied by D is the Dm. This means the total number of available states in the energy range. So this is we also call it probability. How much state can happen? This is the Fermi factor. So the Fermi factor and the energies are related to the this graph. So the number of electrons and the positive 4 are related to this equation. 1 minus Fe is equal to probability of positive 4. The Fermi level is the energy where the probability of electron states are occupied. So the variation of Fermi level with the temperature. Temperature change, so the electron state level can also be changed. So that we draw the energy diagram for the intrinsic semiconductor, anti and the p-type semiconductor. So those are the lecture, and then I do the sum of the tutorial questions.